So, surprisingly, this talk is not going to be about deep learning. We're quite shallow people. So this talk is about dimensionality reduction for symmetric positive definite matrices. So first of all, why do we care about SPD matrices? So SPD matrices appear in several computer vision problems, and here in particular we focus on the problem of visual recognition. And for this task, region covariance descriptors have proven to be quite powerful representations. So region covariance descriptors are computed by extracting features at different locations in an image and then computed the covariance matrix of these features. And so if you have enough observations, then the resulting descriptor is an SPD matrix. So if you want to make these descriptors more discriminative, then you typically want to use high dimensional features in the first place. Now, unfortunately, if you have high dimensional features, then you have very large descriptors. And these descriptors can be very hard to handle. So in this work, we propose to reduce the dimensionality of very large SPD matrices. And more precisely, given a set of images that belong to different classes, we'll represent each image with an SPD, a high dimensional SPD matrix, where here the color indicates the class. And we'll learn a mapping from these high dimensional matrices to lower dimensional SPD matrices, such that the distance between these matrices is a better representative of the class label. So one difficulty that arises when handling SPD matrices is that they form a Riemannian manifold, and therefore they have a nonlinear structure. So this means that the Euclidean distance is not a very accurate measure to compare two matrices. Instead, one would like to rely on the geodesic distance, which is the length of the shortest curves that joins two matrices. So several methods have been proposed to account for the non-Euclidean geometry of SPD matrices. And these methods typically follow two different approaches. Some of them rely on tangent space approximation, so they approximate the manifold by Euclidean spaces either locally or globally. And others embed the SPD matrices to a higher dimensional Hilbert space where Euclidean geometry can apply. Now, in both cases, the problem is that the computational cost of these methods increases with the dimensionality of the SPD matrices. And so typically in practice, people will use low dimensional descriptors that are potentially less discriminative. So instead here, we propose to reduce the dimensionality of large SPD matrices while preserving or even increasing their discriminative power. Of course, there's been other works on dimensionality reduction of SPD matrices. However, they typically adopt the following strategy. So given high dimensional SPD matrices, they'll first map these matrices to a high dimensional Euclidean space, and then from this Euclidean space, they reduce the dimensionality to another Euclidean space. And so this is, for instance, the case of principal geodesic analysis, which is a generalization of PCA to Riemannian manifolds, and PGA first maps the matrices to the tangent space around the Karscher mean of the data. And so it's also the case of covariance discriminative learning, which also approximates the manifold with its tangent space, and then finds a discriminative Euclidean subspace of the resulting Euclidean space. So here, in contrast, we propose to map high-dimensional SPD matrices to a lower-dimensional SPD manifold, where the distance better encodes the notion of class labels. And so our finite representations still are SPD matrices, so they still benefit from the same useful properties, and they can be used in conjunction with existing manifold-based techniques. Now, before going into the details of our method, I will first review some concepts of the Riemannian geometry of SPD matrices that will be useful for our derivations. So first, we'll rely on the notion of distance between two SPD matrices, and in practice, we'll consider two different metrics on the manifold. The first metric is the affine invariant Riemannian metric that was introduced by Pennock and colleagues in 2006, and that induces geodesics on the manifold. The second metric is the Stein metric, and it has the advantage over the AIRM of being faster to compute. Now, in the paper, we also show that these two metrics are related in the sense that the length of any given curve is the same under both metrics up to a scale factor. So in the remainder of this talk, I will use the notation delta to indicate the distance between two SPD matrices, and this delta can be obtained with either of these two metrics. Now, these two metrics also have another interesting property, which is that they are invariant to affine transformation. So if we consider two SPD matrices X and Y, and if we multiply these two matrices from left and right by a square invertible matrix M, that is M in the general linear group, then the distance between the two resulting matrices is the same as the distance between the original matrices X and Y. And so this is true for both metrics, and we'll use this property in our formulation. Okay, so now let's go into the details of our approach. So recall that our goal is to map a high-dimensional SPD matrix X to a lower-dimensional one, f of X. So here, we parameterize this mapping with a rectangular matrix W, and we obtain the low-dimensional SPD matrix by multiplying X from left and right with W, as illustrated below. And so if W has full rank, then f of X is also a symmetric positive definite matrix. So now we define a mapping, but now we want also to define a cost function to learn the parameters of this mapping. So here we rely on the following intuition. We would like the low-dimensional SPD manifold to have a distance that reflects a notion of affinity between the high-dimensional SPD matrices. And so for each pair of SPD matrices, Xi and Xj, we'll write the cost Jij, which is a product between an affinity measure, Aij, and the distance between the two matrices in the low-dimensional manifold. So this means that if we have a high affinity Aij, then we'd like to have a small distance after mapping the matrices to the low-dimensional manifold. And in contrast, if we have a low or a negative affinity Aij, then we're happy to have a high distance between the two matrices after mapping. So in practice, we'll use the class labels to define the notion of affinity, and we'll set Aij to 1 if Xj is a nearest neighbor of Xi from the same class. So that means that our cost function will try to favor pulling together two samples that are of the same class. And in contrast, we'll set Aij to -1 if Xj is the nearest neighbor of Xi from a different class. So that means that our cost function will try to separate two matrices that are of different classes. And finally, the affinity will be set to 0 if Xj is not a nearest neighbor of Xi at all. So now we've defined a cost function, but this is not enough because, as I said before, to have valid SPD manifold, we also need W to have full rank. So here, what we do is we enforce orthogonality constraints on W. Now, this may seem like a too restrictive assumption because, in general, not every full rank matrix is an orthogonal matrix. However, we can show that these constraints entails no loss of generality. And the reason is that any full rank matrix, W tilde, can be decomposed into a product of an orthogonal matrix W and a matrix M in the general linear group. And so because of the affine invariance property of our metrics, then we'll have that the cost function Jij of W tilde is exactly the same as the cost function Jij of W. So we can only enforce orthogonality constraints and not lose anything. So now we have a cost function and we have constraints on W, so we can formulate our learning problem. And so given a set of high-dimensional SPD matrices, learning is expressed as minimizing the sum of all pairwise cost functions such that the resulting matrix W is orthogonal. And because of these orthogonality constraints, this can be a problem, an optimization problem on either a Stiefel or a Grassmann manifold. And the difference is that for the Grassmann manifold, two matrices that are the same up to a rotation actually correspond to exactly the same point on the manifold. So to study whether we want to use a Stiefel or Grassmann manifold optimization approach, we need to study the effect of rotations on our cost function. So if we take any rotation matrix R, the affine invariance property of the matrix also yield that the cost function Jij of W is exactly the same as the cost function of the rotated matrix W. So it means that we can make use of optimization methods on the Grassmann manifold. and in practice, we'll exploit the conjugate gradient descent method on the manifold. Okay, so now we have an approach that can map high-dimensional SPD matrices to a lower-dimensional SPD manifold. Now, on this low-dimensional manifold, we can still learn different classifiers to do visual recognition. And so in our experiments, we tried two different such classifiers. The first one is a nearest neighbor classifier on the low-dimensional manifold, and this classifier evidences the benefits of dimensionality reduction more clearly due to its simplicity. It also can exploit both the affine invariant Riemannian metric and the Stein metric. And the second classifier that we used is the RSR classifier that was introduced by Mertas at ECCB 2 years ago. And that classifier exploits the notion of sparse coding on the manifold, but it was designed for the Stein metric, so the results reported for this classifier will only rely on the Stein metric. So in our experiments, we evaluated the following methods. First of all, with high-dimensional SPD matrices, we evaluated the two nearest neighbor classifiers. We also evaluated the RSR classifier as well as the CDL method of Wang and colleagues. And then, of course, after our dimensionality reduction, we evaluated the two nearest neighbor classifiers as well, and also the RSR classifier. So, as a first experiment, we tried our method for the task on material recognition. And to this end, we used the UI-UC material dataset that was introduced last year at CVPR. This dataset contains 18 classes, and we're using 10 different partitions between training and test data. And the input to our algorithms are high-dimensional matrices of size 155 by 155 that were computed as region covariance descriptors of SIFT features and color features. And the parameters of our approach were obtained by cross-validation, and these parameters are the dimensionality of the low-dimensional manifold, the number of neighbors of the same class when building the affinity matrix, the number of neighbors of a different class when building the affinity matrix. So here are the results. So the first baseline SD was the result reported in the paper that introduced the dataset, and was 43.5% accuracy in terms of recognition. And then we evaluated CDL and RSR on our high-dimensional SPD matrices. They both achieve about 52% accuracy. And finally, the nearest neighbor classifiers on high-dimensional matrices only achieve about 35% accuracy. Now, what is interesting is that after reducing the dimensionality, if we apply the nearest neighbor classifiers, then we increase the accuracy by more than 20%. So we reach 58%, which means that we even outperform the CDL and RSR classifiers that were computed on high-dimensional matrices. And so finally, if we evaluate the RSR classifier on the low-dimensional manifold, we reach the top accuracy of 66.6%. As a second experiment, we performed action recognition from motion capture data. And for this, we used the HDM05 dataset. This dataset contains 14 different actions, and we used 2 subjects to train our method and 3 subjects to test it. And in this case, there are no images. There are 3D joint location of human skeletons. And so the input high-dimensional SPD matrices are 93 by 93 dimensional, and they are covariance descriptors of the 31 3D joint location of the human skeleton. And the parameters of our approach were again obtained by cross-validation. So again, the results on this dataset here, CDL performs 79.8% accuracy, which is slightly higher than the RSR classifier, and this is in both cases on high-dimensional matrices. The nearest neighbor classifiers both perform about 60% accuracy. And now again, if we use the nearest neighbor classifier after dimensionality reduction, we increase the performance by several percentage. Now in this case, unfortunately, we don't reach the performance of CDL and RSR. However, if we use RSR after dimensionality reduction, we reach the best accuracy of 81.9%. So to conclude, we have introduced an approach to mapping high-dimensional SPD matrices to lower-dimensional and more discriminative ones. And this yields a practical way to handle large SPD matrices with existing recognition algorithms. And so in the future, we plan to extend a framework to using different cost functions, and for instance, to handle the unsupervised scenario or the semi-supervised scenario. And we'd also like to study if the concept of reducing the dimensionality from one manifold to another manifold could apply to a different type of Riemannian manifolds. Thank you for your attention.
So could you explain why you got better results after you produced the sparse, smaller matrix?
Well, so the intuition would be that because we're also encouraging the low-dimensional representation to be more discriminative, then it will already better reflect the notion of classes, so it'd be, the task would be easier for the classifier.
Right. Here. Hello.
Yes.
So in effect, you're building a new descriptor, right? So by mapping to this new space, and so I'm wondering whether there's any intuitions that you have about the new descriptor.
Yes. So you can think of the new. We're discussing this in the paper, but you can think of the new descriptor in the case of covariance matrices. You can think of the new descriptor as also being a covariance matrix in lower dimensional features. And so ultimately, yeah, this is really the intuition behind this, is that we'll try to learn. You can think of it as having lower dimensional features that are going to be more discriminative when you consider the covariance matrices.
So in relation to the previous question, maybe you get better results because your mapping, you take into account the distance between the classes. So have you tried to do your mapping from one dimension to the same dimension and see if that improves?
So we did not try this, but so the baseline CDL, the CDL baseline also tries to separate the classes in a related manner as what we're doing. So in a sense, I think there's more to it than just that.
I wonder how you deal with permutations. Is the rows and columns of matrices are in correspondence? Are you invariant to row and column permutations?
Yeah, I think you can show that it's also invariant to row and column permutation, and so yeah, that's why. Yes, I only talked about rotation, but it's also true for permutation of row and column.
Are there more questions? If not, then let's thank our speaker again.
Thank you.